Okay, I think we'll get started. So for those who don't know me, I'm Jeff Rozatarski, and I'm a fourth-year PhD in the HCI. I work with Nikki Gatur, who's up 2 floors, and I do crowdsourcing and data viz work with him. The topic of today's lecture is going to be not completely interaction techniques, but more kind of how do you do research? What is research about? Because this is really relevant to the homework you're going to be doing / have already started. And so to start with, just so we're all on the same page, I'd like to go over the homework a little bit briefly, just so we know what's currently in it, kind of what our expectations are. So the homework is to evaluate pointing devices. And so we've got mice, we've got touchpads, we've got touch devices like iPads or tablets that all point slightly differently. And the question is, what works best? And best can mean different things. So in the homework, you're going to be getting 2 different pointing devices. This could be, for instance, a mouse and a touchpad on your computer, or your computer with a touchpad and a smartphone. 2 very different pointing devices. And the point is you kind of want them to be different so you can see what differences happen between them. And you're going to really pick anything you want within reason. We have a whole bunch of examples here. Anything from like a pointing stick in an IBM computer. If you've got a pointing stick, by the way, by all means use it, because not many people do have these anymore, and they're really, really interesting. So pick 2 devices. You can do a few more for extra points if you'd like. And once you've picked those, be sure to put them into the spreadsheet we have. I can see a bunch of people still haven't, so by all means, please get on that. And so the idea is we can figure out kind of what everyone's doing, make sure we have a good distribution of devices, and you can see what other people are doing too to get ideas. You're also going to do this with 3 different people. Because this is science, you don't just want to test things on yourself, because you obviously are unique. You want to be able to generalize a little bit. So you're going to get 3 different people to do this. Yourself, someone who's like you, a classmate, a person in your dorm, someone who's similar to you but not you. And also someone who's not like you. So this could be someone who's much older than you, someone with very different skills from you, someone who doesn't know how to use a computer. So this is kind of a very different case. It'll be really interesting to compare the data then and see how they use these pointing devices differently from you and your friend. We've created some testing software to help facilitate the pointing. And this is still in development, right? So in iPhone, there are currently some bugs which I'm going to be working on fixing later this day. And if you find bugs in the software, by all means, shoot me an email or drop by office hours. I'm happy to kind of work through them and figure out what's going wrong. You should also look at your data and make sure it's giving you data that's reasonable. You'll sometimes see the phrase too big in the data it gives you. This is because certain tests may be too big to run on your device. So if the test is 10 centimeters wide and your device is only 5 centimeters wide, it's not going to be able to run the test, so it'll just skip it. So I'm going to go ahead and run the test, actually, because we may as well see what it looks like. You're going to put in your name. This is just so we know who's who. Put in your device. So this is a MacBook Pro Retina with touchpad. And be really specific here, because you want to, as scientists, give as much information about your environment as you can. And so I'm going to use with thumb clicking the pad. So I'm not just tapping, I'm actually having a second finger clicking it. I've already measured this, and it's roughly 32 by 20. Be very specific. Include decimals if you've got them. I'm just, for the sake of this demo, not going to bother. If you're using an iPhone or any kind of mobile device, make sure you close the keyboard before you press start, because that can mess things up. Once you begin the test, we're actually going to get into the pointing task. The first 5 are practice, as you can see here. And the idea is you want to, as quickly and accurately as possible, click between these. They'll flash green if you get it right, red if you get it wrong. And as you go between different tests, the bars will get wider and skinnier, and the ribbons will get farther apart or closer together. And so the idea is we can kind of evaluate how well you're pointing and how quickly you're pointing by whether you're hitting the bars and how quickly you do it. When you're done with all this, it's going to spit out a bunch of data at you, which you can either copy into Excel or copy paste and kind of email to yourself. We'll get to that later in the lecture. Once you have these data, you're also going to want to talk to your participants, so the other people, and have them fill out a questionnaire. This is to get an idea of who they are, their level of expertise with the program, how much they enjoy pointing on it. So you can imagine an untrained user may have a very hard time with a touch device at first, like a tablet. One thing I might suggest as you're designing these surveys are something called Likert scales. That's Likert. These are kind of a standard way to run surveys that give you really formal questions give you good results, if I can make a suggestion, but you don't have to do that. The deliverable for this homework is a report. So you're going to enter your data in on a form, just so we have it and we can kind of aggregate it and study the whole class. But you're going to write a report. We want you to describe the pointing devices, so you know what is your environment actually? What are these people pointing at? Who are the people? And where are they pointing in? So if you've got a tablet, do you have it sitting on a table? Are they holding it? Because that can really change things. It can really make it hard to compare between people if you don't know about it. The big part is presenting your results. We're not asking for a formal statistical analysis here. We just want to know kind of general findings. Who was faster? Who made more errors? Did certain participants do better than others? It doesn't need to be completely rigorous like a stats class may demand. The final bit is where you can be a little bit more creative in the sense of you get to discuss your results. So this is very high level. What are the design issues regarding pointing devices? Did you notice anything when people were using the mouse or tapping with regards to how that pointing goes? What are the trade-offs with using touch versus using a mouse? We want you to relate it to history. So we've got 2 really good papers here that study different ways to point. And it's really interesting to relate these to past studies. How does this compare to a joystick, which was previously looked at? And finally, optionally, you can talk about future work. So this may inspire you to investigate other things. What do you think you'd like to study? What other ideas do you have? And of course, include a blank copy of your questionnaire because we need to know what kinds of questions you asked. And it's worth checking and giving you feedback on. So that's hopefully a really quick run through the homework. The idea is get some pointing devices, get some different participants, have them try pointing and see who points better, see what device points better, and see which one's more accurate, those sorts of things. So, changing gears once again, let's jump into what research actually is. Likely this can be review for some of you. I just want to make sure everyone's on the same page with regards to kind of academic research and production research. If you look online, you'll get definitions like this. Research is the systematic investigation into and study of materials and sources in order to establish facts and reach new conclusions. Rather than really dig into that, let's just identify some themes. So research involves systematic investigation. This means that you're not just kind of looking at something and just saying, oh, it looks like that. You're actually following a series of steps. You're being very careful and very organized in looking at a question. The goal is to discover new facts, or if you're not discovering new facts, affirm or deny an existing theory. So there may already be some idea about how the world works. You could try and confirm or deny it. In the case of pointing devices, you can imagine that a lot of people have already investigated mice. So it's interesting to see whether your findings line up with theirs. In HCI, this affirming and disproving existing theories doesn't happen as much as discovering new things, but it's worth mentioning. The overarching goal, of course, is to extend knowledge, whether that be about the brain, about culture, about how computers work. It can really be a variety of things. I put generalizable in parentheses because not all research is generalizable. You can imagine being in a corporation and do research on a particular product. You're following a systematic set of steps, but you're doing it about a particular product, and it doesn't really extend to the full world. You can't say all web browsers act like the one I studied for this company. On the other hand, a lot of HCI researchers, like a lot of people in our department, try and make a point of making our research apply very broadly. So the work I do on one particular visualization, I work really hard to make sure it applies to all visualizations if possible. An important thing to note is not all scientists look like Marie Curie in a lab with this weird barrel thing doing hard science. You'll end up with people like Jacob Nielsen, who does user research. And what he did in the 90s was basically have people lay out cards to try and figure out how to organize websites. This is right when the web was really nascent. And so he'd say, how are you going to navigate a corporate website? Well, let's lay out cards and figure out how that really should be. This is research too. It's a little bit more production, not as generalizable. But this is much more along the lines of usability research, which we're more familiar with in HCI. If you're in the master's program, you will become very, very familiar with usability research, I have no doubt. So at the core of research is the research question. You have something that you're actually interested in studying. And research questions, it turns out, are not easy to make and are quite kind of deep in the way they're structured. So we have a simple question like, do students work harder to perform better in school? And this is nice because it has a direct comparison here. We've got better. So we know after we're done whether there's a better or worse at the end. It's kind of a quantitative thing. Similarly, more in an interaction techniques way, you could imagine, is it easier to get to items in a radial menu versus a right-click menu? That's another general question you could be interested in and actually answer. You can also be a little bit less specific and quantitative. You can be much more qualitative. So this question, how do people hold a mouse and which way is most common, isn't really about better or best or any kind of comparison. It's just about seeing what's out there, identifying themes. This is more commonly called qualitative research. It happens very commonly in design, and you'll probably get some exposure to that in the HCI program as well. Inquiry is a really important step because things like this, how do people hold a mouse, can feed a lot of future research and future quantitative research. So going up a step, in general, research questions come from existing knowledge. You start from something you already know, or you have a hunch about, or already has been covered by research. And then you stretch out to find something new. Ideally, these research questions can actually be answered. So they should be limited enough that when you're done, you can actually say you've answered these. You can end your paper saying, yes, this happened. Yes, it's better. Yes, I found these different ways people hold mice. A point that people often neglect is this question of, is it worth answering? Research questions, a lot of times, you have to demonstrate why this matters. So the question about, do students who work harder perform better in school? This has great meaning to the people in this room. I think we can easily justify why that has value. But there are a lot of research questions that don't have value and therefore may not be worth studying immediately. A good analog to research questions is thesis statements in writing. So in kind of writing an essay, you give your thesis statement to organize your thoughts and declare what you're going to be talking about for the rest of the paper. It's a similar thing in research. You give a research question to identify what you're going to be researching and why it matters. So I'm going to open it up now, and what do you guys think the research question is for our homework? Anyone? Yeah, so when you say dominant, what do you mean?
It's the most used one.
And that's a good one. So between mouse and another device, which is most used? That's a good research question. It's limited, but it's specific enough because now we have most used, which means something. Better can be good, but it may be not specific enough. Go ahead.
Which one's more accurate?
And what do you mean by accurate?
So the test is just click the right line. So obviously since like maybe the iPad or the little red points, and one of them might be more accurate.
Great. That's perfect because we have kind of the binary there of which one of these two. And so those are some ideas of research questions, which are broad, and I'm forcing you guys to get more specific because it leads us into our next section, which is hypotheses. So if you've got this kind of general research question, which has very general terms in it, you may then wonder, well, how do I actually do this? A general question is hard to answer. Let's be more specific. So if we take that research question we had from a while ago, students that work harder will perform better in school. Just like I was doing now, you ask yourself, what does it mean to perform better? Well, what does it mean to work harder? And from that, you actually develop hypotheses. You may not have just one. You may have a whole bundle of them. So in this case, we built this hypothesis. Students that spend more hours studying textbooks will receive higher grades. And so what we're doing is saying, work harder really means more hours studying textbooks. And perform better really means receive higher grades. Now you can imagine if I was writing a research paper about this, no one would probably believe me with just that hypothesis there. Because reading textbooks is not the only part of studying and knowing and working hard. What you'd probably end up doing to answer this research question is coming up with a variety of hypotheses to test all at once. How much are they going to office hours? How much are they doing homework? All sorts of other things relating to not just grades, but maybe how much they learn afterwards through a test. And so hypotheses in general contain a prediction that's testable. And when I say testable, I mean you can kind of do an experiment and have an answer to this. Is it true? Is it not true? Ideally, like research questions, they come from past knowledge. So your hypotheses have to be grounded. You can't just come up with something out of the blue and hope that it's just going to work. It should come from kind of existing knowledge. It should be based on observation. So you can't just come up with a hypothesis that you yourself can say, oh yeah, that's obviously true, that's done. It has to be based on something you can observe and study. You have to use specific measures. So it can't just be things like better or it's going to be good. It has to be very specific, like more hours. This is for quantitative research. Qualitative research has hypotheses that are a little bit different than this. I'm kind of jumping over that because it's not as relevant to our homework. But for the purpose of kind of interaction techniques, these are the kinds of hypotheses we'd be thinking about. They're usually affirmative, and what I mean by that is they usually have positive words. So you could imagine reformulating this as students that spend few hours studying receive bad grades or worse grades. That's an equally valid hypothesis, but in general, by convention, we don't do negative words like that because they can invite some problems later on in the process. It's better to kind of be positive and say more and better rather than less and fewer. Just as a general rule of thumb. This is not a thing you should always do. It's just more of a general rule of thumb if you're first getting into it. And as I said before, there's often more than one. In fact, it will be rare to end up with one hypothesis out of a research question if you're doing it right. So on that note, any more hypotheses coming out of our homework then that you guys may have thinking about it now or have already kind of thought about? Yeah, go for it.
So you might hypothesize that users enjoy touch screens more than they enjoy using the joystick on the iPhone.
And why might you think that out of curiosity?
Because people like to be able to touch things.
And I like that because you've got kind of a clear comparison case. In your case, enjoy, you could measure using a survey. So when you're finally kind of digging down to it, maybe you don't just say enjoy, but you say enjoy as referenced by this certain scale that we're using in our survey. Keep going. Yeah.
We make a hypothesis that, for instance, the touch screen is the first device that is substitute for a mouse you're starting to approach that can maybe even exceed it in terms of accuracy versus speed. If you're doing several devices that are sort of related, for instance, the little knob, trackpad, and mouse.
So you're saying that the touchpad may be more accurate than, or touch screen.
Touchpad probably is not.
Yeah. So to reformulate this a bit to be more kind of specific in general, touch screens are more accurate than mice because they perhaps are kind of more tangible or whatever you may say. Anyone else? What about errors? Because the homework tool is not just measuring time spent, which is kind of that. We've got accuracy a little bit. Any other ideas about error rates? One that I was thinking about is the fact that with touchscreens, you don't always know where the pointer actually is. So there's not really much feedback until you actually press down, which may reduce accuracy rate also. So what happens if you don't find anything? So it's entirely possible you run your whole experiment, and this has happened to me more than enough times in the last few years, where you run the experiment and you don't find anything. This doesn't mean that it doesn't exist. So we invoke something called the null hypothesis. The null hypothesis is empty. It says basically there is no relationship between your two things. So in this case, there's no relationship between hours spent studying textbooks and higher grades. This doesn't mean that spending time studying textbooks does not improve grades. All it means is you couldn't find anything. And this is a common mistake people make when they first start doing research, is they don't find anything, and then they assume that the opposite is true. In reality, you just didn't find something. You couldn't prove that particular hypothesis, which doesn't make it false, it just makes it not proven. It's a weird little tiny distinction, but it does matter. Really, though, this indicates a need for future study. And so the reason why a lot of hypotheses are unprovable is because of confounds. And confounds are other factors that might influence the results of your experiment. So you're controlling a bunch of things. You're having different people do different tasks. Some of the ribbons are wide and skinny, and some are close together. They're using a touchpad. They're using a mouse. But there are a million other factors at play, too. How old the people are, whether they've used the device before, what particular web browser they're using. Are they using an iPhone, which currently blows up if you try to use the app on it? And all these can give you bad results. So your study can be poorly designed. Maybe you never wrote down the procedure you were going to follow, and so each time you ran it, you did something slightly differently. And all the slightly different things you did balanced out so nothing happened. You could be measuring the wrong thing. So the question of studying textbook hours doesn't really make sense if the class doesn't have a textbook like this one. It's not always the case that you realize you're measuring the wrong thing until after you're done. A big one is the participants don't necessarily know what to do. So in the social sciences, there's a really huge effort that scientists put forth making something called a protocol, or a procedure that they follow when participants or humans are involved. And that's because people are really hard to predict. You can imagine if you put a person in a room and ask them to use an iPad, one person's going to pick it up and start tapping. Another person's going to leave it on the table and start tapping. With a touchpad, one person may use a finger to click and another to type, or another to move. One person may tap, another person may actually click it in. All these behaviors are valid unless you tell them otherwise. If you have all those happening at once, your results aren't going to make sense anymore. So creating something like a protocol where you know exactly what you're going to tell participants to do, exactly when and exactly how, will help to reduce this risk a little bit. Another thing worth thinking about is that even the act of watching people changes things. So this is something called the psychological observation effect, where if you just tell a person they're being viewed in an experiment, their behavior will change. People will start performing better on tests. People will be much more stringent about how they're moving their mouse to try and click because they know you're watching. Humorously, you don't even need to actually watch them. You just need to tell them you're watching them. So my real point here is that participants make things difficult. There are confounds all over the place that you have to think about. And the key is just to do some really hard thinking before you run your study about what could mess things up. The last one is that some other thing caused a bigger effect than what you were trying to measure. What I mean here is that you're measuring one thing, but maybe there's something else happening alongside your experiment that changed everything, that you weren't anticipating and didn't even know about. So for example, with this students who spend more hours studying textbooks, therefore they get better grades hypothesis, maybe because they're spending more hours studying textbooks, they're not doing other kinds of studying. And it's that other kind of studying that actually matters. It's not the textbook studies that matter. Maybe it depends on the individual. So some people may not get anything from studying a textbook, and you don't think about that at first. And as a result, your results don't show anything because you had some people who gain a lot and some people who don't gain anything from studying. And of course, if you choose the wrong course, you're not going to get any results at all, and that's the third factor that'll just kill everything. Yeah?
Would you have to randomly assign people to study and not study textbooks to actually make an experiment and therefore useful?
Yeah. That's one possibility. So there are two schools of thought on this, which I'll get into a little bit later in the lecture. But the idea is you can either try and show relationships or show causation. So on one hand, you can say that there's an association between studying textbooks and actually getting better grades. And there's another way to do it, which is people who study textbooks more do get better grades. And so they have different levels of strength. You can imagine just watching people get a huge number of students with different classes, different backgrounds, different abilities, look at how long they have the textbook open, and then look at their grade at the end of the class and see if there's any relationship between the two. You can't guarantee that having more hours studying a textbook will actually give you better grades, but you can show that there's a strong relationship between the two. Alternatively, perhaps ethically questionably, we can do more of what you're suggesting, which actually tell people, don't study your textbook at all. And you people do study it and see what happens. Oftentimes, the realities of research and ethics make that not possible, which is why you have to kind of choose the lesser thing, which is just to show a relationship. In the case of our interaction techniques homeworks, you're pretty lucky in that there are not too many ethically questionable things we'd ever ask you to do, I hope anyway. And all the studies you're going to be doing are kind of causative. You can force people to use another device. And when I say force, just ask them to use the mouse instead of use a touchpad. And then you can say, because they switched, yes, they're the same person, now look what happens, and get that kind of stronger result. So on that note, what about our homework? Any idea of some confounds that may happen in the course of doing the work? Yeah?
Could be time of day. Could things like whether the participant is more alert.
So we do know that psychological arousal is related to time of day. This is kind of how excitable and how alert you are. And that does affect kind of your interface performance. Could definitely be affected. That's really good. Yeah?
What about the environment that you work in? So if you do it like in your room where it's quiet, concentrate a lot more, or if you do it like in a university setting where it's a lot more loud, a lot more traffic, you can be distracted.
Yeah. Definitely could happen. So both in kind of this textbook example, that's true, and in the pointing example. You can imagine that attention resources, because a person's being distracted by noise, they can't pay as much attention to the ribbon moving as they need to. Yeah?
Computer speed.
This is something I'm running into with iOS, actually. On the iPhone, it triggers the events for the taps in really weird timings because it's just not fast enough in background tasks interfere and some other stuff too. That make it not as accurate. And I wasn't anticipating that. It's a confound that actually already has hit me, and I'll be hoping to fix this afternoon later. Any other ideas? Yeah.
Some users being left-handed, some being right-handed, so it really depends on which hand they find most.
And so one way you could help try and alleviate that is by getting a good sample of people. So you can imagine doing all right-handers or all left-handers, and just say in the results section, all of my participants were right-handed. I don't know what this would do with left-handed people.
Actually, let's find out how many people in the room were left-handed. Do you use your mouse with your left hand or right hand? Right.
Interesting.
Yeah.
What about touch devices?
Left-handed people I know still use their mouse left-handed.
So you left-hand touch, right-hand mouse. Interesting. How many people ambidextrously touch their smartphone, by the way, out of curiosity? Like, you use your left hand sometimes, right hand sometimes. Okay, I was figuring like 50-50 maybe. So those are things you really should be talking about when you're talking about your participants in the homework. Because these individual differences hopefully don't have an effect, but you never really know. And it's worth being upfront about it when you're doing research and saying, yes, this is possibly a factor. Yeah?
I guess another confound could be like ordering effects, like because we're doing two devices, maybe like the order in which you tell them to test could matter.
So this happens in a bunch of different ways. So in psychology, there are two effects called primacy and recency. Basically, the first thing you see, you tend to remember, and the last thing you see, you tend to remember. And they can kind of overwhelm each other given certain different environments. So for instance, when you have people on the street saying, try this cola, then try this cola, tell me which one's better, they're probably going to pick the first one. That can affect order. Also, like you said, I wonder about training. So, does using a mouse help you use a touchpad better? Anyone have any more ideas about training? I guess I kind of, go ahead, yeah.
Well, like you're very used to one device in particular, and you're just a novice in the other one.
And especially with your participants, right? So if you have one participant who doesn't know anything about how to use a mouse, which would be weird, but could happen, I guess, then their results are going to be very different. And you've got to keep that in mind as you're analyzing the results. And so this, in general, is a practice it's not something that you immediately are good at. In fact, I'm still not good at it now, 4 years into a PhD. It's something you just have to constantly think about and be aware of as you're doing any kind of experiment, is what else could be affecting stuff? What else could be causing what I'm seeing besides the thing I'm trying to measure? An interesting note is this question of why we don't just use pixels when we're talking about these ribbons. So if you've looked at the homework, you'll see it mentions that the little things you're clicking are 0.25 centimeters wide or 1 centimeter wide, and they're spaced 3 centimeters apart. Because we're using JavaScript in a website, it'd be easier actually to say, all right, put them 200 pixels apart, make them 50 pixels wide, done. But there's a huge confound inherent in that where if you have a different device, pixels aren't the same size across the globe. So the pixels on my Retina screen are very different from the 27-inch screen I have at home, which are very different from a smartphone. And so now the size of those ribbons isn't at all comparable when you test it on different devices, which would be really important because you want to make sure that that performance is at least similar in appearance visually. So that was something we caught early and kind of fixed with a bunch of math that we wish we didn't have to do because it's very inconvenient to do all these calculations. And once again, with iPhones, it's biting us because the iPhone does some weird math on their browser window to mess things up. The fun of doing research. I mentioned all these little tidbits because, this is what happens when you do kind of research activities. You come up with all these little tiny things that you've got to fix as you go, and nothing is ever finished. I'll add that proving a negative is really, really hard. So if you wanted to prove that studying textbooks does not matter, it may or may not affect your grade. That's in fact a really hard thing to do. Proving negative statements, this is part of the reason why we tend to say hypotheses should be positive and not negative. In general, this is a minefield. So if I ask you guys to prove that there's a pencil in this room, all I really have to do is look and find some human in this room using a pencil. It's in front of me there, I found it. This is analogous to saying, I tried a bunch of people, looked at how long they were looking at the textbook, and oh look, it does match with the grades. If I wanted to say that there were no pencils whatsoever in this room, Then I've got to look at every single tiny corner under the desks all over and say, oh, yep, there's no pencil. I'm certain now. I probably even have to look up there because someone inevitably has thrown one up there. This is problematic, and it means that you have to be really careful when you're asking these questions to make sure you don't run into the situation where you can't really prove what you're hoping to prove. Coincidentally, this is what people during the Renaissance used to try and prove that God existed. Look it up online, it's really interesting. It's the anthropic principle. So, inevitably you're going to be actually looking at variables, right? So we've kind of already looked at these in formulating hypotheses. And the idea is that as we convert this general thing, work harder to perform better, as we convert these to hours studying and grades, we're generating variables. These are things we can actually measure. And the key is that these should be specific and match with our research questions. So we kind of already covered this, but the idea is we want them to actually be measurable. So better often isn't a good enough thing to say. Effort often isn't good enough. You want to be really specific and actually something that you can measure in some way. For quantitative research, that means measure with a number. And like the confluence section illustrates, we don't want them to be too dependent on our participants. So even the textbook studying example, you could argue is too dependent on participants. But for instance, percent notes highlighted. I never highlighted notes in college. It just wasn't a strategy I used. That one's so dependent on personal ability and personal ideals that it would be a very bad variable to use, for instance. Not to say that highlighting notes is a bad thing. It's a good thing. I just didn't do it, and some other people don't. So you end up with a couple different kinds of variables in your work. The first variable is what we call the independent variable. This is the thing that you're going to be changing. Think of it like the input. So you put something in, participants do something magic, or your system or the world or whatever it may be does something. Then you get something out, which is the result. So what you put in kind of is the explanatory variable. So it's going to explain what's starting to happen. And in this case, that means hours studying. So I can look at how many people or how many hours people study and use that to try and say, all right, based on how many hours they studied, what is their resulting grade? So what about our homework, the pointing homework? What do you think the independent variables are in that? What are we changing as input and hoping that we see differences in the output? What was that? Yeah, so the pointing device. So whether it's mouse or touchpad is an independent variable. Any others? And really, this one's kind of subtle. So another independent variable, which we kind of did for you, was how wide those ribbons are and how far apart they are. The program kind of automatically changes them for you, but you can imagine putting new levels of those in, trying different ones. And if you're really, really interested, this isn't for extra credit or anything, but you can actually dig into the code of that tester program, and there's just a little list with the different measurements in it. If you want to try even wider bars to see what happens, or even further apart ones, you can do that. And so those are another independent variable because we're actually, alongside the pointing device, we're testing a bunch of different widths and distances too. So on the other side, you've got, yeah.
There's one more.
Oh, is there? What did I forget?
Well, there's
Oh, yeah. So participants, right? You could argue that maybe the similar, dissimilar you participant, for your 3 participants is one, but it doesn't really capture it. I think Brad's getting at the kind of training or experience level. So that third person who's not at all like you could be a person who doesn't use a computer at all. We're not manipulating that. So one common thing you see when you see independent variables is that they're being manipulated. The experimenter's changing them. But you can also think of something like how much a person knows about computers as an independent variable, just one that we can't change directly. The only way you can really change it is by getting different people in your group to test. Yeah?
What about the repetitions you have to do in this code?
Yeah, so that is separate. So the repetitions we're doing is purely to try and get towards a reasonable result. So if you do 1 repetition, it tends to not be as predictive as if you do 20. And so that's commonly thought of as something separate from the independent or dependent variable. It's just repetitions.
Would be something you consider if you were looking at training time, learning effects. So then, you kind of expect people to get faster and better over time. So then it would be an independent variable if you're saying, let's look at the first 5 trials, let's look at the last 5 trials, and see if they're better. Like in terms of repetition, people are going to not do it exactly the same speed.
We also want to know, are they, let's say,
Exactly.
or
So, yeah, so like Jeff was saying, you have a trade-off between learning effects and fatigue effects, recency effects and, saliency. All these things trade off against each other. You kind of have to figure out which ones seem to be the most relevant to this.
And so to illustrate that, this is from the Stu Card paper that was assigned for today, which admittedly is really dense, and hopefully if you look at it again now, more things will be clear. But here's a case where, like you said, the number of repetitions actually is an independent variable. So on the x-axis of the chart is kind of more and more trials, so they're not experienced here, very experienced as they go to the right. And up here is kind of how quick they're doing it. And so you can see the mouse user gets better and better. They get quicker and quicker as these hours and hours and days of going like this occur. So that is a case where they would use it as an independent variable. So the dependent variable is kind of the other side. So it changes because of the independent variable. It's the output, in other words. And this is sometimes called the explained variable, to go with the explanatory variable of the independent variable. Pretty confusing, but think of it as kind of the second half of your hypothesis. It's the grades in this case. So you change hours studying, or you look at hours studying and see how it changes, and the grade is what results out of that. So kind of repeating it, what do you think the dependent variables are in our homework? Go over it.
Error rate?
That's a good one. There's another one too. Yep, time. And so we were spitting those right out of the program as kind of how long they take and how many errors they make. And that changes because of the pointing device, and it changes because of who's doing it. That's commonly how I try and figure out what the IVs and DVs are, is, what am I changing and what's changing because I changed something. There are a bunch of other variables and factors that also factor in. So I had this little hypothesis here, kind of students who spend more hours studying textbooks will get better grades, but there's a ton of other little factors afterwards that I'm also controlling or thinking about. So now I have the institution, they're going to be at CMU, they're going to be a particular course, they're going to have different majors and different study habits, which are going to vary. And so they can be differences between your participants, like what they're good at, whether they've got training or not. They can be differences in your environment. So you can imagine for some reason, if it's really hot in the room, people point worse. Maybe because like sweat on the touchpad or something ridiculous. And there are all sorts of other factors too. Some of these are really advantageous. So if I let people have different majors, then when I'm all done, I can see whether people with certain majors had a better time when they looked at textbooks than other majors. So sometimes it's really nice if you've got a lot of people in your study to actually see, because they have some slight differences, whether those differences make an impact, and kind of keep them variable. Whereas something like institution, I really don't want to test people from different colleges. That'd actually be really awesome, but in this case I want it to kind of be generalizable to the people within CMU. I want to know whether if I meet a student at CMU, I should tell them to study their textbook. In this case, keeping it to only CMU students makes sense and kind of keeps those confounds down. And so what about some other factors in our homework? I think we've talked about a few of these, but if anyone's got other ideas, I'm all for it. And here's some kind of guidance. We've got people, environment, and some other ones. So we already talked about with people, kind of their level of training or experience, so how much they've used a mouse already. We also talked a bit about kind of their level of fatigue currently, both of which we're not going to really control for especially. Anything else about the people that you think may be interesting? Age is a good one. So we already know that older people have very different pointing performance. It's actually different enough. A former student of the HCI used pointing performance to figure out whether a person had disabilities, for instance, or was old age, based because they would kind of point differently. What about the environment? Any other ideas? We talked about noise in the environment a little bit as potentially disrupting their attention. Any other ideas about that? Another one could be kind of what they have to put the device on, where the device is located. So, me touching a device up here with my arms raised, standing, is very different than you guys sitting down with a laptop in front of you, kind of in this position. Similarly, the tablet on the table, or not. Yeah?
So maybe something as simple as just like junk lying around, so a clean area versus a dirty area.
Yeah, I have no idea if that would affect anything, but it definitely varies. and you should think about it. Yeah. All right, I'll scoot ahead then. So presumably you've actually looked at your variables, you've figured them out, you've created some hypotheses, and you've run your study now. And you've got some results. This gets back to the question earlier about, well, why don't we tell people to study and not study, so we can actually say for certain, hey, these people actually did better. This gets at the question of whether your findings are correlational or causational. So correlations describe a relationship. So it's kind of a weak relationship. When something goes up, another thing goes up. Whereas causations actually have a cause and effect. There is a flow. If I change A, then B happens. So you can see the causation is much stronger than the correlation. So what if I told you that wearing stockings causes cancer? This is an example Brad gave me that I really like. If you look at correlational data, in the 50s and on, it happened. You wear stockings, you get cancer. But it turns out it's a correlational finding. What happens is when stocking use went up, smoking use went up. And that's because after the World War II ended, people started wearing stockings and people started smoking. It just so happens they happened at the same time. And it's easy, especially if you're, for instance, a member of the news media, to decide that because this goes up and this also happened to go up, they must be related together. So these correlational findings are iffy. They're not bad. You see them all the time in science. But the thing you have to pay attention to are confounds or third factors. It's that same problem of maybe something else actually caused it. So the reason that stockings cause cancer is not because they both actually are causing each other. It's just they happen to be related to cultural changes, which are the real cause. And cultural shifts are the third factor here that explains what happened. So for example, maybe because we were having people spend more time studying, they got tired faster so they went to bed early. Because they were going to bed early, they did better in the class. So it wasn't actually the textbook thing that actually produced better grades. It was us making them tired and making them fall asleep earlier. That could easily happen, and in fact has happened in studies that I know of, this sort of problem. So whenever you're doing kind of a relationship type study, you've got to be keeping this in mind. What else could be causing this? And whenever you're reading the news, for instance, think about this one a lot, because journalists of science everywhere make this problem all the time, almost to an embarrassing degree. Luckily, in our class, for the most part, we're going to be doing causation. So this is where you can really affirmatively say, because X went up or because X happened, Y must be going up or Y must happen too. So you can imagine, because I had people use a mouse instead of a touchpad, they had lower accuracy. You know for certain it's the fact that they're using a touchpad that caused it. Now I say for certain, but in reality, as we've been talking about, there are other factors that may influence it. So maybe it wasn't that they used a touchpad, it was because they were older. So you have to be really careful here. You need to experimentally isolate everything and make sure that your variables actually are kind of unique and separated from confounds. So this isn't always ethical or possible. Getting back to the question earlier, do we really want to force students to look at their books and force a group of students to never look at them, which is what you need to do to make causational findings about looking at books causing higher grades. This is a subtle issue, so I'm going to stop for a sec and see if there are any questions about what I've covered so far. Cool. All right, so the next step is actually running an experiment, which it turns out is also not easy, as I think I've alluded to already. This on the screen happens to be one of the easiest studies to run. This is a study where they're trying to figure out how thick the chemical pitch is. It turns out pitch is almost completely a solid. It produces a drop like every 50 or 60 years. So they just set up this bell jar, keep it isolated from third factors, and wait for a drop to fall. They've got an easy job. We in HCI tend to have a very hard job because we deal with people. This is much easier to control than participants, as I've said earlier. So in general, the questions you should be asking yourself when you run an experiment is, how do we handle the independent variables? How are we going to separate them out? How are we going to make sure they're really distinct and people know what they're doing? How do we measure the dependent variables? So are our measurement systems accurate? You can imagine with that case of measuring how long people are studying textbooks, you could actually stand over them and use a stopwatch to figure out how long they have the book open and are reading it. That actually would be not bad, but they're going to be where you're looking at them. You could imagine instrumenting the book so it knows when it's open and closed and times it and sends it off to a server somewhere and stores it for you. The problem with that, maybe they could leave the book open then. So there's no answer, there's no perfect way almost all the time to figure out how to measure something. You just have to figure out the right way given your constraints. So with this Fitts law tester, we're using kind of a JavaScript way to measure time, which we know isn't perfectly accurate, and we know has some problems, as we've already seen. But it's kind of a decent way to measure the dependent variable, so we're just going to kind of accept it, given that we know the limitations, we can talk about them a little bit. And of course, as I've been saying over and over again, you also need to think about confounds constantly as you're running an experiment. Think about these third factors, or things that may affect your results negatively. And finally, analyzing your results is a whole other art, which I'll talk about towards the end. So finding the right people for an experiment obviously isn't easy. Waldo apparently is in this image somewhere. I didn't have enough time to figure out where the heck he was, but my point is, if you're looking for a very specific kind of person, it's often very difficult. So for instance, there's a group of HCI researchers who study blind or vision impaired people in a certain age group, and they have a very hard time finding the right participants for their studies because they're looking for a small percentage of the country and then a smaller percentage of that. In your case, it's much easier because you're looking for people at CMU, you're looking for people who are like you, and luckily we've got a ton of those people in this room right now. So this varies, but you need to be thinking really closely about where your participants are, what do they have kind of with regards to the characteristics, are they trained or are they untrained, and make sure you're getting the right people. If in doubt, a lot of times you can say, maybe you'll just find a good enough random group that all those things are going to average out. Psychology does this a lot where if you get enough people together, all the little unique things about them tend to average out when you evaluate all of them together, and it becomes a decent enough story that it's fine. So for example, if you have half people trained, half people untrained, if you average the results together, it's going to be about even, and you don't have to worry about it anymore. Don't worry too much about this for the sake of our homeworks, but it's something to keep in mind, kind of how you do your participants. There's some ways to find participants that are worth mentioning, just in case you're wondering. You can recruit your friends and family, but the big thing to worry about there is something called homophily. This is a psychological term where your friends and family are kind of like you. You make friends because they're like you, therefore your friends are like you, which means they can sometimes be bad study participants. Because if you're just studying yourself and your friend group, they're all going to be similar, and there's not going to be enough differences to really get out all the possible effects. There's some participant pools in CMU you could use. You probably don't have direct access to them, but you could talk to people and get access. Things like the CBDR pool. Some people use Mechanical Turk, which is a crowdsourcing platform for this, which are also pretty good. You shouldn't need to use a study large enough for this class to ever need to go to the bottom two. It's fine just recruiting friends and family. We're not worried about it too much. You can also pay participants, but that's, in fact, really hard sometimes. So in practice, when I've been running surveys trying to pay people, I get maybe 20% to 40% response rate at the most. On Twitter, it ended up being like 5%, and you're spending money to send these tweets to people. So it can be really iffy, and a lot of times you have to think about IRB. This brings me to another point, kind of going back to how hard it is to run an experiment and not think about all the confounds. It's really good to kind of go down this list if you're running a really hard experiment. Start with your friends and family to make sure it works, make sure your procedure is good, and then move to the more advanced things with more people that cost you more and are harder to do to get the scale you need. So you can get 1,000 paid participants, but if you haven't tested it on your 5 friends, you may make a mistake that just ruins all the data. This is going to be jumping a little bit, but when we're talking about independent variables, a lot of times we need to figure out how to set up the conditions. So conditions are combinations of the independent variable. So pretend I'm doing a much simpler version of the homework. All I'm doing is changing the device a person uses and changing how big the ribbons are. I'm not moving them around or doing anything like that. In this case, I have 2 different independent variables, kind of which device they're using on the y-axis and how big the ribbon is. And this means I have 4 different conditions. So in other words, I have 2 independent variables, each with 2 levels. 2 times 2 is 4. So you can do these in a variety of ways. If you don't have a lot of people, but you have a lot of time, you can do something called a within subjects experiment. This is where all participants do all of your conditions. So if I have 4 different combinations, each person does all 4. And this brings up the question earlier about ordering. So you'll notice here, one person uses touch first, one person uses mouse first. This is really important because maybe using touch first does give an advantage for some reason towards using mouse. So you have to do some counterbalancing. What other downsides do you think exist for using kind of a within subjects group, having all your participants try everything? Any ideas? So one big one is just time. Within subjects experiments take a long time just because you're running so darn much. What's an advantage of running within subject experiments? Yeah.
You need to find fewer subjects.
Yeah, that's a really good one. And there's another advantage too, which is the individual difference advantage. So you can imagine, because everyone's doing all the tests, you don't have to worry about some people doing some tests that are really special. You know, these are the trained people, and they just happen to all get the mouse. And the untrained people just happen to all get the touchpad, and therefore your results are messed up. Because everyone's doing everything, it's all even, in other words. But there is the alternative, which is between subjects, which is kind of the opposite in some ways. So instead, you have participants do some subset of the trials. So maybe we split the participants up into different device groups. One person uses touch, one person uses mouse. This is between subjects. So you can imagine within the tests are within the subjects, between the variables are between the subjects. And so just to go through it again for the sake of clarity, what are some downsides of between subjects? Just reverse the advantages of within subjects. Anyone? Yeah, so you need more people, and is there any other problem with between subjects? Which I already kind of mentioned earlier, but we'll repeat it again because it's important. Yeah. Yeah, so confounds, because of differences not percolating across all the conditions then. Advantages then?
If your test is spoiling in some way, such that you can't run it multiple times on the same person, then you have to do it this way.
That's a really good one. So a lot of psychological studies, which involve deception, are ruined after the first time they're used. The person already knows the secret. Now it's funny because a lot of those, even if the person knows the secret, they still work, but there are enough of them that you can only really run them once and you have to do between subjects design. Also, you just have to run fewer studies in the sense of you have two participants, they don't have to be there as long. Not run fewer, have shorter studies. You run fewer studies within subjects because there are kind of fewer people. Anywho, which do you think our homework is, within subjects or between subjects? Anyone? Yep, that's it. Everyone has every exposure to all the conditions. They see all the different ribbon levels, all the widths, all the distances. They try both devices. Therefore, it's within subjects. We mentioned training earlier. As you know, some people are trained, some people aren't. That's why I don't call it an independent variable, because even when we're doing within subjects, we can't really have people who are trained and have people who are untrained and even that out. It's kind of a separate thing entirely. So just a few more guidelines on running an experiment. Please don't follow this comic if you're going to be writing this write-up. He recommends just add some images in an intro, it'll be fine. So I'd suggest that you follow a strict procedure. So as I said before, weird things can happen when you're running experiments. Just forgetting to say one word in a psychology study can ruin your result, for instance. You need to revise your instructions constantly. Even if you think they're perfect, do it again. And you should have instructions written down that you're going to be giving to your participants, because you want to make sure every participant is exposed to the same thing. It removes a big confound that can cause a lot of problems. And as always, be aware of the confounds that are happening. They're always going to be there. They're going to come up all the time. So just be constantly vigilant about it. As far as analyzing your data goes, I wish I could just tell you what to do. There's a whole class on it in the HCI called Applied Research Methods, ARM, which goes into this in great depth. But it really just depends on what kind of question you're asking. Sometimes you don't even need to do a statistical analysis like you might see in a paper with significance values and all the fancy graphs. Sometimes it may be good enough to just say, in general, these numbers seem to look better than these. And for the purposes of our homework, that's really the analysis we're looking for. We don't need you to open up a stats program like R and do an ANOVA to prove that this is higher than this with huge statistical certainty. Because guess what? With 3 people, we probably can't do that anyway. We're fine saying these look more accurate, these look less accurate, and here's my reasoning for it. These could commonly be called descriptive statistics. They don't really compare anything, they just describe stuff. There's no toolbox in general, but there are a lot of really good tools to use. Jump is my favorite in the sense it's GUI-based and really clear what's happening. You can still make mistakes and do terrible things, but it's much harder. R, SPSS are really powerful, but they're harder to use. There's a website called the R Cookbook that has all sorts of formulas for analyzing different data that's really helpful. And a couple of universities have really helpful data analysis guides that you can use as well. And the biggest thing, which it's sad it's at the bottom because I think it's the most important of anything, maybe the most important in this lecture, at least as far as running experiments goes, make sanity checks. So as you're going, look at your data, make sure your data look reasonable. Some people were already doing this with regards to the FITS tester app. So some people noticed it was giving too big for tests that clearly should fit in the screen. And because they noticed that, they knew their data wasn't good, and therefore they shouldn't analyze it. We should figure out what's going wrong in the experiment first. And they emailed me, and I was able to fix the bugs then and improve the experiment. I can't tell you how many times that's happened in my own research, where I've looked at the data, realized I made a mistake, and luckily I was doing it right after I tested it with friends rather than paid a bunch of people to try it out. So I was able to catch it and improve it. So sanity checks, very, very important. If your data don't look right and don't fit intuition, first make sure you're doing everything right, then figure out what new thing is happening. Because you may have discovered something really exciting, but the odds of that aren't high compared to making a mistake, I hate to say. So as I said, as far as the homework goes, don't worry too much about loading up R or Jump or any of these programs. Descriptive statistics are fine. I'd like you to relate them to the FITS law, which we're going to talk about in a little bit, and relate them to the readings, which we mentioned in the article, or in the homework assignment. Really, we're looking for kind of deep understanding rather than the ability to run a perfect experiment, but we'd like to at least see some evidence that you're trying to follow some rigor. It does not need to be a conference paper or anything that fancy. And you don't have any psychologists you're trying to convince that this is true. They're much harder when it comes to statistics than either Brad or I are ever going to be. So that ends the bit on kind of research methods. And I'm happy to talk about this in much more detail. We cut probably 20 slides because A, I like to talk a lot, and B, this is a really complex subject. So I'm happy to go over more stuff if you want during office hours or email me, whatever it may be. Any questions about this kind of researchy segment before I get into FITS law? Cool. Okay, so FITS law. This is a law that's been around for a very long time, and it's concerned with pointing. So how quickly can people point to targets? And there's a field that's very concerned about questions like this. It's called human factors. It's also sometimes called ergonomics. They're sometimes used interchangeably, sometimes not. Some people get very angry if you call one ergonomics. I don't even know how to explain why they think they do. But anyway, human factors is generally just how do we design systems that match human capabilities and limitations to improve performance. So the big one of human factors is we've got an airplane cockpit. How do we make sure we design all little dials and controls and sticks so that the pilot doesn't make a mistake? This is kind of the canonical example. And if you take the HCI class human factors, about half the class is studying aircraft accidents. It's not as macabre and scary as it sounds. You kind of look at an accident, figure out what went wrong cognitively in the instruments and the systems, and then come up with recommendations. So Paul Fitts in the 50s wanted to know just how quickly people could point to things. Because obviously this is important if you're trying to get people to point to tasks, to know kind of a theory of how quickly people do it without having to have a person do it for you. Can we come up with a formula that at least estimates what people really do? And so this is actually from his paper. He had a stylus in people's hands along with some other tasks, I think like moving a disk across. And the idea was you tap, then you'd move, and tap, then you'd move and tap. This is very similar to what you're doing on the FITS tester app. And he was just curious how quickly people could move, find the target, and click on it. Those 3 steps. And this involves kind of 2 parts. One half of it is kind of the physiological brain side of it. So there's a certain amount of processing your brain has to do to figure out where the target is and how to move your hand to the target, which is a fixed cost. No matter what device you're using, you've got to think about it and move to it, or at least tell your nerves to send the signal to move your hand to it. There's also the physical process itself of actually moving and pointing. So these kind of combine to get you the pointing performance. This is important because no matter what device you're using, the cognitive stuff's still going to happen and be fairly consistent. The stuff that's going to change is the physical difference, actually moving the hand, moving the stylus, or moving the mouse, which you can see are kind of different gestures. If you look at how people actually do pointing, and I recommend you try this sometime, just on your own informally, open up your computer and try it. People point in a very interesting way. What they do is, if you're here now, kind of in this corner, the lower left, and you want to get to the upper right corner, you start by making really big movements. But because you're making big movements, you're not going to be accurate. In general, whenever you move your hand a lot, you're not going to be accurate. If you move it a tiny amount, you're going to be accurate. So what the brain does is start with big movements where it knows they're going to be off, figure out how off it is, then make a smaller movement, figure out how off it is. And gradually you make smaller and smaller movements until you've hit the target. If you look at this image on the right, this is a person actually using a laser pointer to point towards a target. This is from the laser pointing paper that was required. And so you can see they start here with the yellow, big movement, adjust, big movement, adjust, big movement, a little bit smaller movement, adjust, smaller movement, and now they're here. Interestingly, if you look at this paper, the pink line here, kind of this magenta, is when they're trying to put their finger off of the button. It turns out the laser stays on for a little while when they're trying to lift their finger, and it goes out of accuracy because it turns out it's really hard to stay pointed when you're trying to lift your finger up too. If you think about the physiology of the hand, it's really hard to do that in and of itself. I recommend trying this sometime. It's really interesting. You can definitely see something in it. Anyway, this is Fitt's law, which looks really complicated, but it actually is pretty easy. So T is the time in seconds it takes to point to something. So this is kind of, that Fitt's law tester gives you a time. It's basically that. A is this fixed cost to start and stop moving and click. So no matter what, you've got to start to move the mouse and you've got to click. No matter which direction you're going, no matter how far you're going, you've got to do these things. So that doesn't really, the distance of the ribbons and how thick they are doesn't matter when you're clicking. It's just how long that takes. But there's also this inherent speed factor. So B is sort of how quick your device is, how good it is at pointing. That's kind of perhaps taking it too far, but it's kind of just this inherent speed factor. It's this inherent efficiency factor. The big log section is this fancy computation to get the index of difficulty. What it basically does is combine the distance between the ribbons and their width, or in general, kind of the distance to the target and how big it is, and give you an estimation kind of in a simple scale how difficult that is to do. So what Fitt was trying to do is create a really general linear equation, kind of algebra style, that measures a fixed cost, how quick the device is inherently, with some kind of general scale of difficulty for how difficult the pointing is going to be. The rule of thumb with this formula is if you double the distance, you've got to double the width. So this guy here, which has really wide bars, is the same index of difficulty, ID, as this narrow one because they're closer together, but the bars are half as wide. So basically, this is a way to level very different pointing tasks. Either it's far away or it's really tiny. They both are kind of comparable. And so when we dig into this Stu Card paper, really now, you can start to see what he's doing. So down here is this log index. You'll note that he uses log 2 d over s plus 0.5. In my slide, I have 1 here. This is a weird little difference. You can calculate this index of difficulty any way you want. Originally, Fitz did it this way with the 0.05. He thought that was a good way to do difficulty. Since then, a person named Shannon and a bunch of academics since then have said 1 is probably a safer bet to use. Just keep that in mind because if you're trying to compare your results to different papers, you need to figure out which version of this index of difficulty they're using. And they will mention it because it's one of those things. So if we look here, we can actually see the Fitts law equation for what he discovered to be his mouse. So he had a bunch of people do it, and he charted it out. So Over here is really low index of difficulty. These are really giant targets, or they're really close together. And over here on the far side near 6 are really tiny targets or really far apart targets. And as you'd expect, big targets or close targets don't take very long to point to. Far away targets are much harder to point to. They take longer. And you'll note it starts somewhere here. It doesn't start at 0 because, as I said, you've got to spend some time clicking and moving the mouse. It's interesting to think that these people took almost a second before they started moving the mouse and before they finished clicking. You wonder if maybe that was because the mouse was still a little more nascent than it is now. I don't know that I buy that, but it's interesting to think about. So you can actually do this with your data. The same thing that's charted here, you can do if you so desire. Now, we're not collecting nearly as much data as Stu Card did. Remember, he kept participants in a room for like 4 hours doing this, and then had them come back the next day and do it some more. So that's a ton of data. With 3 participants doing kind of 20 trials of each condition, it's just not very much data. So it's not going to be super accurate. But anyway, let me demo briefly how to do this sort of thing. Taking your data from the fits tester all the way in and creating a chart like what we saw. This is going to be pretty quick, so by all means, check out the video again or stop by office hours if it doesn't make sense, and hopefully it'll be a little more clear. So when you finish the fits tester, it'll give you this really long kind of comma-separated thing. The text at the bottom that says copy CSV to clipboard. If you paste this into a file and save it as something .csv, you can open it in Excel, and it'll become a table. So if I do that, for instance, let's shift this over. I'm going to double-click on this, and you can see now I've actually got a table. And you can see there's my name. I'm testing it on myself, and I use this mouse at this level of DPI. Apparently, I was playing a video game, so I said DPS. And then you can see each column has an average time. So this 0.25 centimeters is how wide the bars were in that condition. 1 centimeter is how far apart they were. And so you can see the average time in milliseconds was about 200. Normally, I deleted them already, but you'd also see error percentages for each condition right next to this. And so what you can do then is delete the errors, because we don't really want to chart the errors. We're going to look at them elsewhere. We really only care about the times. You can select all of these and do a copy. And if you go down to a clean part of your spreadsheet and do paste special, there's a really cool button no one knows about called transpose all the way down here. And that will flip your results across the diagonal. So now they're like this, which is much, much easier to deal with. And would have saved me a lot of time in high school had I known about it then. Perhaps embarrassing. So there we go. We've got our time. What I'm going to do is start building a new chart. So I need to record kind of the width and the amplitude, which is kind of that distance factor. So this is 1, 2, 4, 8, 1. And I'm getting these numbers from kind of the condition that I recorded over here. And so this is 2, 4, 8, 4, 8. The reason why, for instance, you don't see a 1 here is because if 2 centimeter bars were only 1 centimeter apart, they'd overlap each other, and therefore it wouldn't be a valid test. Because I was using a really big 27 or 24-inch monitor, all the tests were able to complete. You don't see too big in any of these columns because it couldn't fit. I'm also going to put in the widths. Sorry, this is a bit tedious. So now what I'm going to do is calculate the index of difficulty. So remember that formula we saw earlier? So I'm going to create, it's the log of the distance, which is going to be f6, this guy, over the width, which is e6. I'm going to use the one from the paper, which is plus 0.05. And it's going to be base 2. Remember, it's log base 2. The reason it's log base 2 and it's kind of this fancy 0 through 6 scale is because it relates to information theory. If you know any information science, it's kind of the bits being processed by your perceptive and physiological systems, which is weird, but it makes more sense if you've done info sci, which I really haven't done. So now I'm going to copy this in, and you can see here's the index of difficulty for all these different trials, which is pretty cool. Now I'm going to do time, and it's in seconds, remember. I want to compare eventually to this chart, which is somewhere in cards paper. I want to compare eventually to here, and you see it's in seconds there. So I'm going to do equals this guy divided by 1,000, because there are 1,000 milliseconds in a second. So if I do this, now I can actually chart. Sorry for the Excel lesson. It's pretty silly, I know. And I think I actually have to do it this way because I want a scatter chart. Or apparently this doesn't work. Anywho, let's go to the version that's already been done. So I went and created a scatter plot. And what you can do is you can see already that as index of difficulty increases, these tend to go up. And if I want to create that formula just like Stu Card did, I can add a trend line, which will fit a line to this chart. And I want to display the equation. And there you go, there's my line. And if you look at this equation, it is 0.1x plus 0.1. So x in this case is the index of difficulty. If you go back to this paper, you'll see his is 1 plus 0.096 index of difficulty. So what this means is I was roughly the same, my kind of mouse input was roughly the same speed or efficiency as Stu Card's mouse, but it took me far less time to click and start moving. Which isn't that surprising because I'm really, really used to that mouse. I've had it for years. So you can see that you can kind of create these charts pretty organically just using Excel and get the formula you may be interested in. I demoed this, but you don't have to do this. It's just something kind of if you're interested and want to compare the results, you can by all means try it out. By all means put it in the paper too, but I'm not going to give you extra credit or anything for it. It's just really interesting. So final takeaways, keep in mind that all the papers that we're having you read have collected a ton more data. They had people paid to do this, taking data. Some of them were in corporations, so they kind of threw ethics to the wind in some ways. I don't like the idea of keeping people clicking for 4 hours. It feels like RSI may happen or something. If you get a null hypothesis, that's okay. So if you can't prove something definitive, that is okay. Ideally, tell us what you might expect to happen, why your hypotheses were such. Why did you expect the touchpad to be better, even if you didn't prove it was better? And give us some reasons for why you think you may have gotten the null hypothesis. Don't just say the tool sucked. Give some more details as to what went wrong, and hopefully contact me before if possible. Check out the error rates. They're going to be really interesting. We had some interesting hypotheses already in the class about them. And look at the laser pointer paper again. Especially now that you've gotten kind of this research methods overview, you can see how the paper is breaking it down into those different sections. See if you can pick out where the research question is in the laser pointer paper and where their hypotheses are. If you look at a psychology paper, they'll almost always have that RQ colon and the research question, H colon and their hypothesis. Most HCI papers don't tend to do that. Yeah?
How did you get the data for the width and amplitude? Is it the same for everyone?
Yeah, so it's the same for everyone, and it's kind of already part of the columns. So if you want to, so behind the scenes, if you look at your data, we basically just get it in. It's part of the columns. So you see this is 0.25 width by 1 centimeter. And it mentions that in the results screen. So I just copied those in. If you're really adventurous, once again, no extra credit for this, but if you're interested, by all means, try it. If you go into this Fitts Law app, way at the top of the JavaScript, here are actually all the experimental conditions right up at the top. So if you want to try different bars, want to try different widths, by all means, change these up, see what happens. If you find bugs, by all means, let me know too. I would love that, but you don't need to do that. So here's Stu Card, by the way, in the middle, looking dapper with Bill Curtis and Alan Newell. Newell is one of the people who this building was named for. Really great guy, good papers. You should read about him. Also read about Simon, too. He's really cool. Questions about homework 1?
So the app that you have coded for us to run the experiment will give us that data that we can
Yeah. So the end screen will give you a table that you can look at, and it'll also have that kind of comma-separated stuff that I showed that'll look like this, which you can just paste into a file and save with this .csv end, and you'll be able to load it up in Excel.
Can you set up a sample Excel?
Yeah, I'll copy. So this doc I just made, I'll copy and put online with the slides. You don't have to obey this format, but it may help you kind of figure out what's happening.
And for your report, it'll certainly be more interesting to try and compare the different devices. So if you look in the laser printer paper, it has charts for the speed and the error rates for the different devices. So that's something we are, want you to look at, see if there's any differences. And this, there is a way to take the same data and make a comparison chart too?
Yeah.
In the card paper, I think the card paper has different.
So you could imagine doing mouse here and then copying more data here for touchpad and kind of creating two different colors of series here if you wanted to look. Also do it for your participants too if you're interested. Another thing you can do is treat all of your participants as the same person and average their values together or keep them separate. What I would do is just for each participant, if they're all using the mouse, just copy them one after another down here and put all of the points together in a chart because you'll have more data then. And maybe you'll get a more accurate line.
So some people have, about 11 people apparently have already finished this part of the experiment. If you use an iPhone, chances are your data's all messed up because we've been discovering bugs along the way. If you feel like redoing it, that's fine. If you don't want to redo it,
Just make a note, yeah. Just make a note that it wasn't working in your homework and kind of make the best of it anyway. Don't throw up your hands and say, it didn't work, therefore I'm not doing the results. That's not going to fly. Cool.
Any questions?
Is the width and the amplitude randomized in the board?
Yeah. So that
It's going to be different.
Yeah, so it randomizes the order at each time you load the page. So it theoretically shouldn't have an order effect with any luck. You can turn the randomization off if you don't like it for some reason, but I can't imagine why. If you're using a mobile device, make sure you close the keyboard before you press the start button. For some reason, the browsers do really weird things when the keyboard's open. I don't know why. And if you have any other ideas for the app.
It's designed to be done sideways. Whichever way's
Good
the
call.
long way, right? So on a phone, it's sideways. On an iPad, it's also sideways. Right?
Yeah, let's go to that. So there's a little note here. Make sure you read the entire thing, by the way, before you start running experiments, just so you know what you should be looking for. But right here is run your device to the longer dimensional horizontal, so be in landscape mode no matter what. And close the keyboard. And if you're using a desktop computer, make sure you maximize your browser to give the most possible screen real estate you can. You're going to measure the screen. The screen is what we care about, but make sure your browser is as big as it can be too.
It would be fun to do this one, and you have to run it back and forth.
Anyone wants to?
Somebody had a question?
Can you send an email on the iPhone survey?
Yeah, so I'm going to get to it this afternoon, basically either during office hours if I'm not too busy or right after, and I'll try and send a Blackboard right after. Yeah. And sorry about that again for the inconvenience.
And if you find any other bugs, let us know as soon as you can. Oh, the other thing is I started a Piazza discussion group where people like to use that. It's been pretty successful in other classes, so if you ask a question, everybody else can benefit from the question and answer. So I'll invite everybody to sign up for that, and that way you'll get notified their questions.
And the final one, if you're worried about bugs and really just want to make sure you get it done with the minimum amount of trouble potential, using a mouse and a touchpad is the safest option on a computer. It's obviously not the most interesting, but that is the most well-tested and most likely to succeed of all of the combinations.
Have people had success with Android devices? Everybody tried?
Tried Android phone, didn't work, but Android pad is, I think it's just set a view port for the browser.
So I didn't set it to full screen viewport or anything. We're trying to latch on the device view. So we're trying to latch on the device resolution as well as the browser viewport.
So like on the vertical, on the Android pad, I don't see one bar. But it's,
Interesting.
Yeah.
Okay.
It didn't shrink to the extra size of the device.
Okay. If you run something like that, email me and I can send you a debug version.
Okay.
If you're willing to go to the extra effort and we can try and figure it out. The iOS bug may fix that too. It's an issue with how devices scale, but it's hard. You also have your quizzes, by the way. So if you want to pick your quiz today, I'm going to put the grades up on Blackboard when class is over.
They're in alphabetical order here, so.
Yeah, everyone did pretty well. Any questions for grading, stop by office hour. No problem. All right.